How a Beretta 92 works, invented by Carlo Beretta in 1975. Carlo Beretta stands in the Gardone Val Trompia workshop, spring light filtering through tall windows onto a steel workbench. Before him rests a handgun frame with its slide removed, exposed barrel, recoil spring visible through the opening that would define a generation of sidearms. The year is 1975. NATO nations are beginning quiet conversations about ammunition standardization. The Italian military carries the M1951, reliable but aging, and Beretta, a family name synonymous with tools of defense for 5 centuries, must answer a question that has no purely mechanical solution. How do you build trust into metal? The prototype before him looks unfinished. Where other service sidearms present enclosed slides, smooth, complete, visually continuous, this design reveals its interior architecture. A rectangular cutout runs the length of the slide's top surface, exposing the barrel from breech to muzzle. Engineers in the adjacent room debate whether this transparency will be perceived as strength or vulnerability. Procurement committees prefer familiar silhouettes. They trust what looks like what they already know. But Carlo knows something they don't yet: the physics of reciprocating mass. Every time a handgun cycles, the slide must travel rearward against spring tension, extract a spent cartridge, cock the hammer, then return forward to chamber a new round. The heavier that slide, the more energy transfers to the user's hand. The more movement, the slower the recovery between shots. The slower the recovery, the less controllable the tool under rapid conditions. The cutout removes metal where it isn't structurally necessary. Less mass, less inertia, more control. He runs a caliper along the locking block, a component no larger than a domino, yet the heart of the entire operating system. This small wedge of steel, riding on a crosspin through the frame, will determine whether the barrel and slide separate at precisely the right moment. Too early, and internal pressure will compromise the cartridge case. Too late, and the mechanism will batter itself into failure. The tolerance specifications he's written require machining precision, typically reserved for aerospace components. Some colleagues think he's over-engineering a simple problem. Carlo sets the caliper down and reassembles the slide onto the frame. The mechanism cycles smoothly, barrel and slide moving as one, then parting, then reuniting. It works on the bench, but a tool that works in controlled conditions means nothing. The test will come when mud, sand, temperature extremes and extended usage schedules try to break what precision built. And before any of that, he must convince institutions that what looks unconventional is actually inevitable. If stories like this help you see how engineering quietly shaped history, tell us in the comments what surprised you so far, and stay with us for the next chapter. Carlo Beretta was born into an assumption that developing defensive tools was the family trade, not a choice to be made, but a legacy to be carried. His great-great-grandfather Bartolomeo established the Beretta manufactory in 1526, supplying equipment to the Venetian Republic. By the time Carlo was old enough to understand what the factory produced, Beretta had survived 4 centuries of global conflicts, technological revolutions, and market collapses. Survival, he learned early, required knowing when to preserve tradition and when to discard it. His formal training followed the European model: engineering study at university, apprenticeship in the family workshops, gradual assumption of design responsibility. But 1975 presented a challenge unlike any his predecessors had faced. The global market was consolidating around standardization. NATO member states were moving toward the 19mm parabellum cartridge as a common service round. Any manufacturer hoping to secure institutional contracts needed designs compatible with this specification, capable of meeting trials that tested not just accuracy, but durability across conditions no single organization could replicate. The M1951, Beretta's current service model had served Italy well since its adoption. Its locked breech system, using a falling locking block similar to the Walther P38, was mechanically sound. But it belonged to an earlier design philosophy, one that prioritized immediate post-war production over long-term performance margins. Carlo had access to reports from armories, locking blocks wearing prematurely, recoil springs losing tension, frames showing stress near the slide rails after extended service. These weren't catastrophic failures, but they were chronic inefficiencies, the kind that made procurement officers look elsewhere. The pressure wasn't just market competition. It was generational. His father's generation had rebuilt the company after the 1940s, navigating difficult occupations, material shortages, and the weight of past history. Carlo's task was different: to prove that Beretta could innovate, not just manufacture, that Italian engineering could compete with German precision, American production capacity, and emerging manufacturers in other NATO countries. He assembled a small team: metallurgists, machinists, test engineers. The directive was simple: design a service tool that would function reliably after 50,000 rounds with minimal maintenance. Not just function, but maintain accuracy, consistent trigger pull, and parts integrity. The specification seemed impossible. Service tools of that era typically required technical intervention every 5 to 10,000 rounds. Carlo's target was an order of magnitude beyond industry standard. The team began with material science. The locking block, that domino-sized component, became their obsession. They tested steel alloys, heat treatments, surface hardening processes. Each iteration went to the test range, where usage schedules measured in thousands of rounds per day revealed what laboratory analysis couldn't predict. Some blocks showed stress, others wore smooth too quickly. The solution, when it emerged, came from aerospace suppliers: a vacuum-melted steel with controlled grain structure, expensive but predictable. The operating principle Carlo settled on was not invention, but refinement. When the trigger releases the hammer and the firing pin strikes the cartridge primer, ignited powder generates pressure that drives the projectile forward through the barrel, while simultaneously pushing the cartridge case rearward. In a locked breech system, the barrel and slide must remain locked together during this initial phase, unified against the force trying to separate them. Only after the projectile exits and pressure drops to safe levels can they separate. The mechanism that governs this separation is the locking block. Positioned beneath the chamber, it engages both the barrel and the slide through precisely machined surfaces. As barrel and slide move together rearward for approximately 4 millimeters, the locking block rides on its crosspin. Then geometry intervenes. The block's engagement surfaces, shaped as ramps and flats, cam downward. The barrel tilts slightly, disengaging lugs that had locked it to the slide's interior. The barrel stops against the frame. The slide continues alone, extracting the spent case through the open-top ejection port, compressing the recoil spring, cocking the hammer for the next cycle. This tilting barrel system had proven itself in previous designs. What Carlo changed was the execution. The locking block in the 92 was manufactured to tolerances 3 times tighter than the M1951. The engagement surfaces that guided the tilting motion were held to specifications measured in hundredths of millimeters. This precision eliminated the slop, the microscopic play between components, that accumulated into wear over thousands of cycles. Tighter tolerances meant less internal battering. Less stress meant longer service life. The open slide configuration served multiple purposes beyond reducing reciprocating mass. It created a self-cleaning ejection path. Residue that would accumulate in an enclosed slide, carbon, unburned powder, environmental debris, fell away through those rectangular ports. Field inspections required no disassembly. Lift the tool, look down through the cutout, see barrel condition immediately. What appeared to be minimalism was actually functional transparency. But procurement committees in 1976 didn't see it that way. When Beretta presented the 92 prototype to Italian evaluators, the first questions weren't about performance, they were about appearance. The exposed barrel looked unorthodox. Officials accustomed to enclosed slides questioned whether the cutout would allow contaminants to enter the mechanism. One evaluator suggested the design seemed incomplete, as if a cover plate had been forgotten. Carlo responded not with argument, but demonstration. The test protocol was simple. Use the tool, submerge it in mud, use it again, then sand, then a mixture of both. Then extended usage schedules without cleaning, 500 rounds, 1,000, 2,000. The 92 continued functioning. Enclosed slide competitors began experiencing failures as debris accumulated. The open top that looked like a vulnerability became an advantage the traditional designs couldn't match. Do you think this design choice was inevitable or a risky gamble at the time? Share your view in the comments and pass this story to someone who enjoys understanding how things really work. The test phase revealed what specifications alone couldn't predict. Beretta built 30 pre-production prototypes and distributed them to test facilities, academies, and independent evaluation organizations. Each tool carried a serial number and a logbook. Users recorded usage counts, malfunctions, environmental conditions, and subjective assessments of controllability and ergonomics. The data returned to Gardone Val Trompia in weekly batches. One pattern emerged consistently: the locking block, despite aerospace-grade materials and precision machining, showed wear signatures after approximately 15,000 rounds. Not failure, the mechanism still functioned, but measurable degradation of the engagement surfaces. Carlo's team analyzed the worn components under microscopy. The damage wasn't fracturing or deformation. It was erosion, the slow grinding away of molecular layers where steel met steel under pressure and movement. The solution came from an unexpected direction. A metallurgist suggested phosphate coating, a surface treatment more commonly used for corrosion resistance than wear prevention. The coating itself was microscopically thin, barely measurable, but it changed the friction characteristics between the locking block and its mating surfaces. Test blocks with phosphate treatment showed significantly reduced wear after equivalent usage schedules. The improvement wasn't dramatic, but it was measurable. Service life extended from 15,000 rounds to approximately 30,000 before replacement became advisable. This modification exemplified Carlo's design philosophy: incremental optimization rather than revolutionary change. The 92 didn't introduce a new operating system. It refined an existing one through material science, tolerance control, and systematic testing. Innovation didn't require reinventing principles. It required understanding which variables, altered slightly, produced disproportionate improvements in performance. The double-action trigger system added another layer of institutional acceptance. The first shot could be fired with the hammer down, requiring a long, deliberate trigger pull, approximately 12 pounds of force, that both cocked and released the hammer. This allowed individuals to carry the tool with a round chambered safely, addressing concerns about accidental discharges. Subsequent shots operated in single-action mode, the hammer pre-cocked by the slide cycle, requiring only 4 to 5 pounds of trigger pressure. This duality meant the 92 could accommodate different operational preferences without requiring separate variants. Italy formally adopted the Beretta 92 series in 1976. France followed within 2 years, producing it under license as the Palmer's G1 with minor modifications to grip angle and finish specifications. But the validation that would transform the 92 from successful European tool to global standard was still 9 years away, proceeding through bureaucratic evaluation channels with the inevitability of institutional procurement cycles. Carlo knew this. He'd built not just a tool but a platform, a design architecture capable of accepting modifications, accessories, and operational variations while maintaining core mechanical integrity. The United States military trials of 1984-1985 subjected competing designs to evaluation protocols that bordered on destructive testing. The specifications demanded tools capable of cycling 9,000 times without parts breakage, maintaining 4-inch groups at 25 meters after exposure to temperature extremes ranging from -40 to 125 degrees Fahrenheit, functioning after mud and sand immersion, and demonstrating component interchangeability across randomly selected specimens. Beretta submitted the 92F, a refined variant incorporating lessons from 8 years of European service. The modifications were subtle: improved grip panels, relocated release mechanisms, strengthened slide-to-frame interface, but they addressed every minor complaint logged in service reports. The test tools arrived at Aberdeen Proving Ground in Maryland, marked only with numerical codes, manufacturer identities concealed to prevent bias. What followed was systematic stress testing disguised as evaluation. Test protocols cycled tools through environmental chambers, then to firing ranges, then back to environmental stress, then to usage again. Slides showed fatigue, frames showed wear, locking mechanisms wore beyond specification. But the Beretta 92F samples continued functioning. When slide rails showed wear, the tools still maintained accuracy. When springs lost tension after thousands of rapid cycles, replacement springs restored original performance. Parts interchangeability validated not through measurement, but through actual field condition substitution. The decision, announced in 1985, was simultaneously technical and political. The Beretta 92F was designated M9 and selected as the standard sidearm for all United States Armed Forces. American manufacturers protested. Congressional hearings examined whether foreign designs should replace domestic production. Users debated 9mm performance versus older traditions. But beneath the controversy, the engineering was irrefutable. The M9 worked across conditions that broke competing designs. The adoption triggered production scaling beyond anything Beretta had previously attempted. The contract specified hundreds of thousands of units, with delivery schedules measured in years. Carlo's team had designed a tool for precision manufacturing: tight tolerances, controlled materials, careful assembly. Now they had to design production systems capable of maintaining those standards across volumes that multiplied their entire company output several times over. New machinery, new training protocols, new quality control procedures. The design that succeeded in trials had to succeed in mass production without compromising the precision that made it reliable. The open slide design, initially questioned by procurement committees, became the M9's most recognizable feature. Users learned that the exposed barrel allowed instant verification of status, loaded or clear, visible without manipulation. Technicians discovered that the cutout provided access for inspection without disassembly, reducing maintenance time. What had seemed unconventional in 1975 became standard expectation by 1990. The 92 hadn't just entered service. It had changed what service tools looked like. Carlo Beretta retired from active design work in the early 1990s, watching the M9 deploy to every corner where American forces operated. The tool appeared in contexts he'd never imagined during those 1975 workshop sessions. Desert environments that exceeded test specifications, naval vessels where salt corrosion challenged every metal surface, training facilities where new recruits learned not just to operate, but to trust the mechanism under their hands. The 92 platform evolved through variants: rail-equipped models for accessory mounting, compact versions for discrete carry, and specialized modifications with threaded barrels. But the core design, that exposed barrel, that falling locking block, that double-action trigger, remained unchanged. Institutions worldwide adopted it, not because regulations mandated Beretta, but because once users and technicians experienced the system's reliability, they requested it by name. Italy, France, Brazil, Chile, over 90 countries integrated the 92 into their structures, each negotiating licensing agreements or direct procurement contracts. The tool Carlo designed for Italian trials became one of the most widely distributed service sidearms in modern history. The influence extended beyond direct adoption. Competing manufacturers studied the 92's engineering philosophy, the emphasis on reliability margins, designing components to exceed rather than merely meet specifications, became industry practice. The understanding that service equipment must earn institutional trust through transparency rather than mystery shifted how such tools were presented to procurement committees. Later polymer-framed designs, developed decades after the 92's introduction, inherited its DNA even while replacing steel frames with synthetic materials. They prioritized reliability, accepted the falling block locking system as proven, and understood that users trust what they can understand. Carlo's final curiosity, the one that defined his entire approach, was whether engineering could be both rigorous and visible. Could a tool reveal how it worked and still inspire confidence? The answer was written across hundreds of thousands of M9 sidearms in service worldwide. Transparency wasn't weakness. It was clarity. The rectangular cutout that looked unfinished in 1975 prototypes became the signature by which a generation of personnel recognized reliability. You could see how it worked. You could verify it worked. And because you could, you trusted it. The Beretta 92 proved that trust isn't built through mystery, but through consistent performance, measurable precision, and design decisions that prioritize function over tradition. Carlo didn't invent a revolutionary operating system. He refined an existing one with such care that it became the standard against which others were measured. That refinement, incremental, patient, obsessed with tolerances measured in hundredths of millimeters, changed what institutions expected from their equipment. The exposed barrel wasn't a compromise. It was a statement. Engineering works best when nothing is hidden. If you enjoy calm, true stories about how engineering shaped the world, subscribe to the channel, leave a like, and tell us from which country you're watching.